Hello, everyone. Welcome to section 3.4. This section is on the real zeros of polynomials. We will be mostly focusing on the rational zeros of polynomials. So the whole idea of this section and the next one is that we're going to be developing skills to factor higher degree polynomials. So polynomials that are bigger than 3 and 2, which we've been doing so far, but now we're going to develop tools we can start factoring more and more polynomials. So the basic idea of this section is, let's say we have some polynomial in factored form like this. So let's say we've got like a polynomial p of x, and in factor form, it looks like x minus 2 times x minus 3 times x plus 4. That's not very good for. There we go. So when we go ahead and try to expand this out and FOIL it out, eventually, if you go ahead and do all the steps, etc., blah, 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 you probably find that you'll eventually get x cubed minus x squared minus 14x plus 24. Now, the thing to note here is that all the coefficients of this polynomial are integers. The coefficient here is just 1. The coefficient here is -1. This is a -14. And this is a 24. They're all integers. They're not fractions or decimals or square roots of something. They're just regular integers. And the reason for that is because these numbers were integers, right? Because when you go ahead and do the factoring, or not the factoring, sorry, the FOILing steps, you're going to only be multiplying x's by numbers, or sorry, x's by integers and integers by integers. So you're always going to get integer coefficients. And so what we're going to see happen is this next rule is going to allow us to go back the other way. It's going to allow us to say, hey, look, we have integer coefficients. We can say something about the roots. So that rule, that rule that we're going to talk about is called the rational zeros theorem. Okay, so this theorem is a little bit long and it's a little bit abstract, but don't worry, we're going to break it down step by step. So let's say we have a polynomial. So if polynomial, and I'm going to write a general polynomial out. So let's say like it has leading coefficient a sub n. Let's say it's a degree n polynomial. And the next term would be an a sub n minus 1 to the x n minus 1 plus all the way down to a1 times x plus the constant term, a0. So this is our polynomial. And let's say it has integer coefficients. So all these an minus 1, all the way down to a1 and a0. So all those are integers. So 1, 2, 3, -1, -2, -3, 24, 14, they're integers. And the leading coefficient and the constant coefficient are not 0. That's important. Then we can say something. Then every rational zero or root, so every rational root of this polynomial, p of x, looks like plus or minus p over q, where p and q are integers, and p is a factor, so a divisor of our constant coefficient a naught, and q is a factor, a divisor of our leading coefficient a sub n. So that's a lot to process. Take a minute to absorb it. So what this is saying is that if we start with this polynomial here, right, and it's got integer coefficients, and we know that the first one and the last one are not 0, then every rational 0, so every 0 that is a fraction, an integer or whatever, is going to be of this plus or minus PQ form. And we know what P and Q are. They're going to be where P is a factor of the constant coefficient A naught, and Q is a factor of the leading coefficient A sub n. Now, this doesn't tell you that everything that looks like this is a root. That's not what it's saying. It's saying that like these are like all your candidates. So what this is giving you is like a short list, like, hey, here are what the possible rational zeros look like. And so what we're going to do in this section is we're going to look at like what that list looks like, and then how can we check that list to figure out which one of them are actually roots. Okay, so let's go ahead and look at an example. So for example, let's say we have a polynomial like x to the third minus 4x squared plus 3. So here, leading coefficient is 1. The coefficient on the x cubed there, secretly hiding right there. And the constant coefficient is 3. So this was our A sub n, and this is our A naught in the theorem. So 3, or rather, let's say this, 1, the only factors of 1 are 1. And then for 3, 3 has 2 factors, 1 and 3. Okay, so if we want to write out what all the possible rational roots are, we want to combine these 2 factors together. And so we're going to put the factors of the constant coefficient on top and the factors of the leading coefficient on the bottom. And so the way we'd write this is that our possible rational roots are plus or minus, and then we'll do this combination first, 1 over 1, and then plus or minus this combination here, 3 over 1. So secretly there are, this looks like 2 options, but because the plus or minus, you have minus 1 over 1, positive 1 over 1, minus 3 over 1, and positive 3 over 1. So these 4 options are the possible rational zeros of that coefficient right there. Okay, before we get into how to check this list, let's go ahead and take a look at making a list for something a little more complicated. So let's say we have a polynomial like 2x to the 5th plus 3x cubed plus 4x squared minus 8. Okay, so the leading coefficient here is 2. The constant coefficient is minus 8, although because we're doing plus and minus, you don't really have to worry about that. We're just going to focus on positive 8. 2 has 2 factors, just 2 and 1, and then 8 has 4 factors, 8, 4, 2, and 1. Okay, so now we combine these. Remember, the constant coefficient factors go on top, the leading coefficient factors go on the bottom. So we can start with combining 8 with 2 and then with 1. And so we get plus or minus 8 over 2 plus or minus 8 over 1. And then we move to 4, combine 4 with the other 2. So we get 4 over 2, 4 over 2. Don't forget the plus minus like I just did. Plus or minus 4 over 2, and then plus or minus 4 over 1. And then we use the 2, plus or minus 2 over 2, plus or minus 2 over 1. And then lastly, look at the 1 there, and get plus or minus 1 over 2, plus or minus 1 over 1. Now you probably notice there's some redundancies in this list. For example, this 1/1, that reduces to 1, and then 2/2 also reduces to 1. So there's redundancy. That's okay. This is just like what the theorem tells us are all the possible candidates for our roots. So this list is perfectly good for all those candidates. So now, how can we use this to actually find rational roots? So I'm going to go ahead and illustrate this process with an example. And then when we're done with the example, I'll write out kind of the basic steps that you would take for this method. So first, let's look at the polynomial we just looked at, which was the x cubed minus 4x squared plus 3. And then we found that its roots were plus or minus 3/1 and plus or minus 1/1. And I'm going to go ahead and reduce these down to plus or minus 3, plus or minus 1. Now, your candidates won't always be integers. Obviously, if you look at the previous example, you have like a 1/2 here. That's totally okay. It just happened in this case. They just have 3 and 1. Okay, so what we're going to do is we're going to take each of these roots, all 4 of them, because there are 4, and we're going to check if they're roots using polynomial long division and the factor theorem. So remember from last time, the factor theorem says that some number c is a root of your polynomial p of x, if and only if x minus c is a factor. So what that's saying is that if you have c a root, then x minus c is going to be a factor. That means if you divide your polynomial by x minus c, there's not going to be any remainder. And if you divide your polynomial by x minus c, and there's no remainder, so if x minus c is a factor, then we know that c is a root. So we're going to be using that direction right there to check. We're going to be taking each of these numbers, that'll be our c. We're going to divide our polynomial by x minus that number. And then if there is no remainder, it will be a root. But if there is a remainder, it's not a root. Okay, so let's go ahead and see that process in action. So let's check if 3 is a root first. So we're going to go ahead and divide. The polynomial we're dividing is the one we had, x minus 3 minus 4x squared plus, remember, you need to fill in all the spots where there's no x term, where there's a 0 coefficient. Notice there's no like x term here. So we need to put a plus 0 times x and then plus 3. And then we're going to divide that to check if 3 is a root. We want to check if x minus 3 is a factor. So note here that we're using a minus. There's kind of a sign flip here. That's important. Okay, now let's go ahead and do this division. So we're going to be looking at that thing a lot. And we're going to be first looking at this leading coefficient. And we ask, what can we multiply the thing in the blue circle by to get to the yellow one? We're missing like 2 powers of x, so we'll multiply that by an x squared. And we take x squared, multiply it by both the things in there. We get x cubed minus 3x squared. And then we put that in parentheses and subtract it away. We get a 0. That's good. It means we did that step right. And then we get a minus 4x squared plus 3x squared. So that's going to be a minus x squared. Okay. Bring that plus 0x down. All right. And now we're looking at this thing here. And we ask, What can we multiply the thing in the blue circle by to get the thing in the yellow square that we're looking at now? And I think the answer is going to be minus x. Then we take that minus x and multiply it by x minus 3. I think we get minus x squared plus 3x. Slap parentheses around that baby, subtract it away. We get a 0 minus 3x. Drop the 3 down. Do the same thing. Looking at this term, I think what we want to put up here is a minus 3. Multiply that minus 3 through, and we get a minus 3x plus 9. Subtract it away, 0, and then plus 3 minus 9 is going to be minus 6. Uh-oh, so the remainder is not 0. So 3 is not a root. Okay, that's fine. We've got 3 more to check. So let's keep cracking. So checking if, let's do minus 3 is a root. Do that. We're going to do division, a lot of division in this section. So our polynomial is x cubed minus 4x squared plus 0 times x plus 3. Not a very clear 2. There we go. And because we're checking if minus 3 is a root, we want to check if x minus minus 3 is a root. So that's x plus 3. So remember, sign flip. Okay. Again, blue circle. Again, yellow square. What can we multiply x by to get x cubed? I think that is an x squared. Multiply that down, we get an x cubed plus 3x squared. Slap minus signs around it. Subtract it away, we get 0. And then minus 4x squared minus 3x squared is going to be a minus 7x squared. So we're not doing redundant work. We can already see this division is going to be different. Okay, drop down that plus 0x and do the same thing. Okay, what can we multiply x by to get minus 7x squared? I believe that's going to be a minus 7x. Multiply that minus 7x by our divisor, we get minus 7x squared minus 21x. Subtract it away, get a 0, and then a plus 21x. And we drop down that 3. Now we're looking at this thing right here. Okay, we need to multiply x, the thing in the blue circle, by 21 to get to 21x. So we write that up there like that. And then multiply 21 by our divisor, we get 21x. And this is going to be a plus 63. That's 21 times 3. Subtract that away. And you can already kind of tell, yeah, see, that's a minus 60. 3 minus 63 is minus 60. So the remainder here is not 0. So it is not a root. So negative 3 is not a root either. Okay, so 3 and negative 3 weren't roots, but we still have to check 1 and negative 1. So let's go ahead and do that. So let's go ahead and check if 1 is a root. We want to check if x minus 1 is a factor. So we want to divide our polynomial by x minus 1 this time. Plus 0x plus 3. All right. And same thing as usual. All right. I think this is going to be an x squared again. Multiply x squared by our divisor, we get x cubed minus x squared. Subtract it away. We get a 0 here. That's good. And then we get a minus 4x squared plus x squared. That's going to be minus 3x squared. Oh, wait. I think I might have. Nope, that's right. Ignore me. Okay. Drop this down. 0 times x. All right. And now we're looking at this thing here. We need to multiply x, the thing in the blue circle, by a minus 3x to get to minus 3x squared. So we write minus 3x, and we multiply minus 3x by our divisor. We get minus 3x squared plus 3x. Subtract that away. We get a 0 here. That's good. And then we get a minus 3x here. Okay. And then we drop down this 3. All right. Now we're looking at this. All right. I think up here we need a minus 3 to make that x a minus 3x. Multiply that minus 3 by divisor, we get minus 3x plus 3. Something magical might happen. Subtract that away, we get 0, and then 3 minus 3 is 0. Aha! The remainder is 0 here. So in this case, 1 is a root. Cool. And then, of course, we should still check if minus 1 is a root. So let's go ahead and finish this problem off by doing that. We do the same thing again. So because we want to check if minus 1 is a root, we want to check if x minus 1 is a root. So x plus 1. Or sorry, not a root, a factor. Divided by our polynomial. Okay. And we do the same thing again. All right. So as usual, we get an x squared up here because x squared times x in the blue circle is x cubed in the yellow square. So that's good. And multiplying that by our divisor, we get x cubed plus x squared. Subtract that away. We get a 0 here. That's good. And then we get a minus 4x squared minus x squared. So we get a minus 4x, or not minus 4, sorry, minus 5x squared. Drop that down, 0 times x. Okay, now we're looking at this. By the way, when you're doing your scratch work, you don't have to draw these boxes and circles. I just do that so it's really clear like what I'm looking at in this division. You also don't have to do this division with long division. You can use synthetic division because we are dividing by linear factors. It would be a little bit faster, and you're welcome to use it if that's what you want to do. I'm just using long division because it's just more useful in general. Okay, so we want to multiply our blue circle x by minus 5x to get minus 5x squared. So we'll write that up here, minus 5x. Multiply that by our divisor. We get a minus 5x squared minus 5x. Subtract that bad boy away. Get a 0 here again. That's good. And we get a plus 5x. And we drop down this 3. Okay. And we're looking at this right here. And then I think we want a 5 up here to get a 5x. Multiply that through. I think we get a 5x plus 5. Subtract it away. Okay, that's 0. And then 3 minus 5 is negative 2. Okay, so the remainder here is not 0. So that means that negative 1 is not a root. So the roots that we found with this method was 1. All the others were red herrings, so to speak. Okay. Now, this might seem like a really weird and tedious process, like why do we care about finding the roots of polynomials? It turns out that finding the roots of polynomials is going to be a big key step in a lot of the things we're going to do in later sections and later chapters. And it will also be, if you go on to take calculus or higher mathematics, finding the roots of polynomials is something that comes up again and again and again and again. So learning how to factor these things is a very key skill to develop. So let's go ahead and write out like what the steps are for this technique. So how to find roots with the rational roots theorem. So RRT, rational roots theorem. The steps are thus. The first step is to list all possible rational roots using the rational roots theorem. Your second step is then to divide your polynomial by your candidate factors using the factor theorem. So remember, C is a root if and only if x minus c is a factor. And then step 3, if your remainder is 0, you have a root. If the remainder is not 0, you do not have a root. And then step 4 is to repeat steps 2 and 3 for all candidate roots. So those are your steps for the process that we just went through for that one example. Notably, this does not help you find all the roots. It only helps you find the rational roots. So there might be more roots in that polynomial, like irrational numbers or complex numbers, blah, 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 all that messy stuff. So this is just for rational roots. We will go over finding other kinds of roots in the next couple sections, actually. But for now, this is just the rational roots, and these are the steps. Anyway, let me know if any of this wasn't clear or if you want a little extra help. I'll be in office hours as usual, and I hope to see you around.